All right. So I actually don't have something just yet to put in these about sections, but maybe I'll think about something. Okay. But let's talk about the graph here at least. Okay. So linear, right? What kind of graphs do we expect to see for a linear function? So yeah, Chloe. If you really need to, I guess you better go. Yes. All right. Okay. Okay. So linear, folks. What kind of graphs do linear functions have? Yeah, straight line, right? So maybe I'll draw a line that looks, like, oh, come on there, pen. Let's get going here. Okay. So connect the dots like that. We can also do this too, though. Okay. Okay. What kind of equations do we see when we talk about a linear equation? What kind of forms do we have, for example, the linear equation? Okay, yeah, we got the y equals what, though? mx plus b. Okay, so we have the slope-intercept form. Right? But we could also see it in like ax plus by equals c. You guys remember what that one's called? I'll zoom in here some. Standard form. Yep, very good. Okay, that's another form we could see. Excuse me. And then for the equation, there's one more equation here, and maybe this one's like we haven't seen too much of. It's like the y minus y1 equals m times x minus x1. You guys remember what this one is called? It's got a slope and it's got a point. It's called point-slope form. Point-slope form. It's one other way to write the equation of a line. Okay? Okay. What about the table? When we look at a table, for the next one down here, okay, what are we going to see in a table? Yeah.
Ordered pairs that would go kind of in a row, up or down.
Okay, by how much each time?
Same amount.
The same amount each time. Exactly right. So in the table, okay, we're going to see for the x's and for the y's, okay, that the x's and y's, okay, increase or decrease by a constant amount. Okay? The x's and y's, they increase or decrease by a constant amount. Right? And you're adding, plus or minus, adding or subtracting. Adding or subtracting there. Okay, so x's and y's increase or decrease by a constant amount there. Okay, what kind of, it shouldn't be series, it should be sequence. Okay, cross out the word series there, put sequence, sorry. Okay, what kind of sequence do we associate with a linear relationship? Arithmetic or geometric? It's arithmetic. Okay, arithmetic sequences, sorry, not series. A series is when you add the numbers in the sequence. So it's a arithmetic sequence, okay, is what is associated with the linear. Okay. I think I know what I'm going to put in the about section here up here. Okay. So easy, quick and easy, right? The graph is super easy to see because linear means line, right? It's very easy to see. Equations, we're pretty familiar with linear equations, right? Tables as well, right? We're just adding by the same amount. Every time you go up by the same amount in the x, you should go up by the same amount in the y's too. Okay? Same amount each time. And then finally for the sequence, it's arithmetic. That's what it's associated with. For the about up here, let me put something up here. So okay, so for the about, what we're going to put is that the highest exponent, constant amount, yep, constant amount. The highest exponent is 1. Okay, so that's what we'll put there for linear. The highest exponent is 1. Okay, that's another important note there. Highest exponent is 1. Yeah, when Chloe comes back, you can go. All right, now, exponential. We just got done talking about exponentials, or not done. Well, we're pretty much done, right? We're at the end of the unit now. Okay, for an exponential, what's the exponent in an exponential? Or what's in the place of the exponent? What's in the exponent's place? A what? An x. That's right. So the highest exponent is x. Okay? Exponential. X is in the exponent. Okay? For these graphs, there you go, Erica. For these graphs, right, we have curves that look like this. And we have curves that look like this. Okay, right? We have growth and we have decay. Okay? We only really have one equation for I'll get to the paper. We only have one equation for exponentials. Right? What's the one equation that we have for exponentials? Y equals... Well, that's a different thing. I see what you're saying, though. Well, that's for geometric. But yeah, a times b to the x. But then what Trey was saying is he said 1 plus r, and that's not wrong, too. You could also put a 1 plus r or a times 1 minus r. Okay, so you can also put in 1 plus r or 1 minus r in there for the b instead, right? Because isn't that what b is equal to? B is equal to the 1 plus your r or 1 minus your r2. That's fine as well. Sorry, I was going to write a parenthesis there, and now I made a really large-looking a. Okay, that's supposed to be an a. Awful handwriting. This is what I get, though, I guess. Okay. Now, for this table, what kind of pattern or what kind of relationship we're going to see in this table? We're not going to add by the same amount each time. What are we going to do instead? Multiply by the same amount each time. Exactly right. Okay.
Plus r y or x?
It's to the x. To the x. Sorry. Thank you. Yeah. Okay. So, let's see. So let's see here. So as x's increase, you multiply y by the same amount each time. Okay, right? So that's the key thing, right? Linear, you're adding the same amount each time. Exponential, you're multiplying by the same amount each time. Multiply. Okay? Which then leads us to the kind of sequence. What sequence do we associate with exponential? It's not arithmetic, right? Because that was for linear. What's this one? Geometric, the other one. Okay? All right. So far, so good. Lines and exponential there. Am I moving too fast? Anyone need to slow down or anything? Need the bottom part there? Okay. Anyone else still writing there? Are we all good? Move it to the right. So this way? I'll zoom out just one skosh there so we can also get the, maybe get both in. There we go. Okay. You're welcome. Okay, and then for quadratic, all right, what's the highest power we're going to see in a quadratic function?
2.
Highest exponent is 2. Okay, highest exponent is a 2. What is the name, or what kind of shape do we experience with quadratic functions? What kind of shapes do we get? Yep. Yeah, a U or a frown. Yeah, parabola, the official title there. So I'll draw one where it's opening up, like the U at sky. described. We could also have like the frown kind of shape, right? Okay. Remember, we call this is mathematically called this concave up, and then this one we call concave down. Okay, that's what the actual math term is for that. Okay. Now we have a couple formats for this one. Okay. One of the forms we have looks like this: y equals ax squared plus bx plus c. Do you guys remember what is this form called? Ax squared plus bx plus c. Remember what that form's called? Not explicit. Standard form. Okay. We also had this form, x minus h squared plus k. Remember what we called this? The h and the k are what special point on our graph? It's the vertex. So this is vertex form. It tells us the vertex. Right, and we have the 0 or the y-intercept form, and that looks like this. Ooh, I think it was like P and Q, right? Isn't that what we used? Something like that, I think. Okay, so or x-intercept form, if you like. Okay. So again, different formats there. The hardest one to maybe decipher that it's being quadratic. So this one's pretty easy to see it's quadratic, right? There's the highest power, x squared. This one also, you can see that we're going to square that x, so we'll have x squared there. And this one, well, it's a little bit harder to decipher, right? Because if you look, you're like, wait a minute, this x has an x to the 1, this is x to the 1. But if you multiply them, right, you'll get x squared. And so that's why the degree, the highest power there is 2. Okay? Now, this table is probably the trickiest one for us to write like a nice and concise way of describing the table. Okay? So, what's that?
Don't stop beating his hands in.
I got you. Thank you, Alex, for stopping. Okay. So here, what can you look for? Okay, so look for increasing and decreasing behavior. So in other words, you might see both increasing and decreasing. Linear will not both increase and decrease. Exponential will not both increase and decrease. But quadratics can increase and decrease. Okay? You may also see the pattern you may add by consecutive odd numbers. That's another like common pattern you'll see in quadratics, adding by consecutive odd numbers. So in other words, you'll add by 1, then the next one you'll add by 3, and then you'll add by 5, by 7, by 9, and so on and so forth. Yeah, that'd be like a quadratic form. Quadratic pattern there. Okay, because the common, it's like a second difference is constant. So anyway, okay, and there is no sequence associated with the quadratics. Okay, we don't have one. Okay, so quadratic does not have a sequence associated with it. All right. So keep this handy. We're not going to do the back. Just keep this one handy right now, okay? Because we're going to be doing some problems now. So keep that handy for yourself. All right, actually, let me zoom in, sorry, because I bet some of you guys aren't quite done yet. All right. Yeah. Whoops. Let's just do this, I think. All right, Mr. Steve's going to pass out another paper here. We're going to do. Just for some practice. We're going to start on this one right here. Sorry, I'll zoom out some now. Sorry, we're going to start on this side. They are kind of small. You're right. you. All right, so let's take a look here for some practice. We'll do a few together, and then I'll have you guys try some on your own, okay? Yep. Okay, so we're going to keep those papers close by. We're going to use those to help us identify things. All right? All right, so let's take a look here at number 1. Okay, I'm going to call on some folks, too, to make it more interesting, right? So, no. Promise it won't hurt. Well, you have 3 options. So you can guess, too, if you really need to. Can you phone in a friend? This is not Who Wants to Be a Millionaire. Are we ready? You volunteer as tribute? All right, let's go to Lily. Lily, how about this? What do you say? Linear, quadratic, or exponential, Lily? Quadratic. Okay. What clues you in there, Lily? Anything specific? Yeah, I mean, it's parabola. There's no other graph it could possibly, or a relationship there. Yep, it's definitely quadratic. Okay, very good. Let's go to number 2 then. Okay. Let's go to Chloe. Chloe, number 2, what do you say? What about this graph right here? Whoops, I moved it. Linear, quadratic, or exponential? Exponential, okay. Can you further say whether it is exponential growth or exponential decay? Yeah, it's growth, right. Yeah, exponential growth. You can put EG short. And I forgot here, Lily, can you be a little bit more, because it does want us to be a little more specific here. Is it quadratic, is it positive quadratic, or is it negative quadratic here, Lily? Negative, very good. Okay, I'll put an N for negative. Okay. All right, so number 3. Number 3, let's go to Sierra. Sierra, linear, quadratic, or exponential? Linear. Is it a increasing linear, or is it decreasing linear? Is what? Increasing. We're going up from left to right. So this is increasing linear. Okay, increasing linear. We're going up from left to right. All right, do a few more. Let's go ahead and just do the rest of these here. That shouldn't be too bad. All right, number 4. Let's go to Alex. Alex, number 4, what do you say? Linear, quadratic, exponential. Okay, is it exponential growth or exponential decay? Exponential decay. We're going down, right? Very good. Okay, decay. All right, let's go to Braden. Braden, number 5. Linear. Oh, he's not here. He can't answer. All right, how about Cameron? Cameron, number 5. Linear, quadratic, or exponential? Linear. And is it increasing linear or decreasing linear? Increasing linear. You got it. Very good. All right. Number 6. Last graph. Let's go to Tyler. Quadratic. And is it a positive quadratic or a negative quadratic? So it is below the y-axis here, so I think I can see what you're saying there. But the positive and negative is referring to the a value. Remember, the a value determines whether it's opening upward or opening downward. This one's opening upward, so it's going to be positive a value. So it's a positive quadratic. And that wasn't super clear, I think. But I think that's what they're looking for at the positive part. Because you're right, a lot of the graph is below the x-axis there, but I think that's what they're looking for. All right, we'll do a few tables, and then we'll do a few of these functions, and then we'll have you guys try some here on your own. Or maybe we'll just stop with that. We'll see. Anyway.
Number 4,
for exponential decay. Okay, let's look at some of these tables now. Let's zoom in here on this one. Okay, so let's go to, let's see here. Well, Dawson, what kind of pattern do we see happening here? Our x's are going up by 1s, right, every time. Plus 1, plus 1, plus 1, plus 1. But what's happening here? To go from 100 to 10 to 1 to 1/10 to 1/100. We're dividing by 10. So is that linear, quadratic, or exponential? If we're dividing by 10. Or in other words, we're multiplying by the same amount each time. We're multiplying by 1/10, right? Help us out here, folks. What is it? Linear, quadratic, or exponential? Exponential decay. Okay, so Dawson, remember, if you are dividing by the same amount each time, Dawson, that means you're also multiplying by the reciprocal. Okay, so you're good. It's awesome you saw we were dividing by 10, but it's the same thing as multiplying by 1/10. And so it's exponential decay. Okay, because our common ratio there was 1/10. Or you can say the b as well. Well, anyway. Let's just say the b is 1/10. B is 1/10 there. Okay? Let's take a look at number 8. Okay? What's the pattern here? Every time we go up by 1 with the x's, how are our y's changing? Let's go to John. What do you say there, John? Every time our x's go up by 1, what happened to our y's?
Then add it by 3, so it's linear.
Add by 3. Yep. Linear increasing because we are adding by 3. Okay? I guess we say the slope is positive 3 there. Yeah, m is 3 there. We're adding 3 every time. Okay. All right. Let's go to number 9. All right. How about Sky? Sky, what kind of pattern do you see here? Hey. Yes. We will be doing tutoring. Yes. Sorry, decreasing linear. Okay, very good, Sky. How can you tell? What did you see happening here with our y values?
As x gets negative, the y gets bigger.
Okay. And our right, how much is our y value going down by every time? Down by 5. That's right. So it's linear decreasing. M equals -5 there. Okay. All right, how about number 10? Let's go to this one, and then we'll do some functions too. All right, so Alec, what kind of relationship do you see happening here? Okay, you say number 10 is negative quadratic? Okay, what clues you in about that? How are our... Guys, I'm tired of shushing. Really getting tired. I'm getting really frustrated, okay? Can you please just listen in? I don't know if it's a chocolate or if it's because it's the end of the week. I don't know, but maybe this is easy. I hope it's because it's easy. That's what I hope, but I'm concerned it's not. So please, let's listen in here, folks, okay? We still have 20 more minutes. Alex, sorry. What's the pattern here? How do we get from here to here to here to here? Yeah, it's not quadratic, is it? So what can we do, though? 1/3 to 1 to 3 to 9 to 27. What are we doing every time here? Multiplying. Exponential. Exponential increase, or exponential growth. Okay, and so b is 3. Okay, b is 3. All right. A few more here. 11. Let's just do I don't know. We'll do up to 15 or 16 maybe or something like that. We'll see. Maybe just up to 14. That should be fine enough. Okay, let's look at number 11. Okay. All right, Erica, number 11. Linear, quadratic, or exponential? What'd you take?
Quadratic?
Okay, what clues you in about being quadratic?
I don't know.
So you're guessing.
Yes.
All right, so quadratic, we would be looking for if it's quadratic, we'd be looking for an exponent of 2. Do we have an exponent of 2 here, Erica? No, our exponent is what? It's not 1.
X.
It's x. So x is
exponential.
exponential. And
Exponential
is it
growth.
okay? Very good. Now, Eric, how did you know it was growth?
Because I grabbed the one and
Okay,
Yeah.
you graphed it. All right, well, that's perfect. You can type in your calculator and see that it increases from there. But what about just looking at the function here? What about it tells us this is growth? Chloe?
It's
Greater than
1.
1. Yeah, so 5/2, our b value here is greater than 1. And that's greater than 1, so we are growing. Okay, growing. All right, so go to number 12. All right, number 12, let's go to Aaron. Aaron, exponential growth, exponential decay, quadratic positive, quadratic negative, decreasing linear, increasing linear. Let's just focus on, is it linear, quadratic, or exponential first? What is that? Correct, it's not quadratic. Okay. Linear or exponential. Let's just focus on that. So what clues you in that it's linear? Okay, there's a 3 to the x power, but since the x is the exponent, it is what, Jackson? Is it linear or exponential, Jackson?
Linear.
Ooh. Guys, it's exponential. It's exponential here. Exponent. Sorry, Jackson. Did you have a question for me or something?
Is it in y equals?
It's got y equals, but you see it's got the 3 is to the x. It's not 3 times x. It's 3 to the x power. Okay, now, is this going to be growth or decay here?
It'll be decay.
No, it's not going to be decay. It's again growth.
It's again growth. Okay, so Brady, why were you going to say it was going to be decay here?
Because I thought
Guys, listen, please. 3, Brady, right, is what is being repeatedly multiplied, right? 3 to the x. So that's our b value. Okay, b is 3, which is greater than 1, so that means it's exponential growth. Eric was right, okay? The 1/4 is in front there. That's our a. That's our starting amount. We're multiplying repeatedly by 3. All right, let's go to Brady. Brady, number 13. How about this one, Brady?
I think it's quadratic.
Okay, why quadratic?
Or I know it's not linear.
Well, you know it's not linear. Why?
But it is linear.
Well, Brady, you got to tell me. What do you think? Why do you think it's not linear?
Because it's not squared.
Because it has what?
The highest exponent is 1.
Okay, so yeah, the exponent here is 1. But wait a minute, isn't that a clue for linear, right?
Yeah.
So yeah, it is linear. And in fact, this is in slope-intercept form. Brady, do you recognize what's the slope in this equation? It's the -2. So does that mean we're going to be linear increasing or linear decreasing if we have a negative slope? Very good, Brady, exactly right. Linear decreasing. Okay. All right, we'll do 14 here. All right, we'll do 14. I have one more paper I wanted to look at today. I know, very exciting. Very exciting. All right, let's go to Hannah T. Hannah T, number 14. I know you just got in. Quadratic, and is it quadratic positive or quadratic negative? Is the u going to be opening up or is the u going to be opening down? It's quadratic positive. Okay, folks, help us out here. Why is this one quadratic positive? Because what? The a, which is 2, is positive, right? There's our little a right there. Okay, is positive. So a is greater than 0. Yep. Yes, go ahead. All right. Hold on to this paper. I'm not going to assign it for homework or anything like that, but we might do a few more of these. But we might do a few more of these on Monday or Tuesday, depending, okay? I got one more paper here. Mr. Seaver's going to help me pass out, I think. Okay. No, I gave them all away. I didn't get to eat some myself. I'm a little depressed. Last one? Last one. We're finished? Okay, well then, good. We'll go over, hold on to it because we are going to be using it again. You'll be able to check your answers and stuff. Yes, but Trey, you really should make sure you do some homework still that you're missing. Okay, that will guarantee your grade goes up some. I can't guarantee a quick check will be enough, but if you do some homework, okay. You have that. I think I checked that one already. I haven't put it in yet, but you need to do more homework than that. There's plenty for you to look at. Okay, well, you have to do it at home then. Okay. And make sure you get it to me then by on Monday. I can, any assignments that I assign after today will be in term 4, but I can still put grades in on Monday. Okay. Okay, from term 3. I can't just add new assignments, that's all. All right, folks, last thing I wanted to review here today with us All right, guys. Let's take a look here at this last little bit. Okay. Sierra and Kaylee, let's listen up, please. Okay. We have things to do, right? Last little bit today. Now, the reason why I'm going over this is because this question shows up in all sorts of ways, okay? It can really be a part of anything that we've done so far, okay? This idea of average rate of change, okay? That's what we're going to be talking about today. So this is really, we can title this even better, just the average rate of change review, okay? Because we've kind of seen this before, but I don't know if I've ever done a super great job of being very specific about it, so I want to do it right now, even with the 10 minutes that we have left. Okay, so what is average rate of change? Well, the word rate of change, or the phrase rate of change, we've seen that before. It's slope, right? And so average rate of change is just that. It's the slope formula between 2 points, okay? So we find the slope, right, by subtracting the y coordinates and then dividing by subtracting the x coordinates, right? The change in y over the change in x, or the rise over the run, if you like, right? So, for example, for these 2 points, okay, right? How we set it up? Okay, so it'll be, go ahead, 3 minus 2 over 1 minus 5. Okay, that's one way to set it up, right? So again, if we say that's x1, y1, that's x2, y2, okay? You could also say, shh. All right, guys, look, I'm serious. I need you to stop talking. Okay? I'm tired of having to stop. Tired of having to shush you. Okay, I'm feeling real frustrated. If you don't want to learn it, that's fine, but be quiet so other people can. Okay? Or if you're just trying to talk, then talk later when it's appropriate, not when I'm trying to talk. 2 minus 3 is another way you can set this up. Okay, y2 minus y1, and then x2 minus x1, 5 minus 1. Okay? John said this way. Okay, the slope formula technically says this way, but guess what? They're going to be the same thing, okay? It's going to be the same thing. 3 minus 2 is 1. 1 minus 5 is negative 4. 2 minus 3 is negative 1. 5 minus 1 is 4. You see, you get the same thing. 1 over negative 4 is the same thing as negative 1 over 4. All right? That's a slope formula, right? We've done this before. But you can do this slope not just for lines, right? So, for example, this is the slope between these 2 points, right? So you create a line between these 2 points, you get this slope. Okay? But the idea is you can find the average rate of change to find a slope for any 2 points on any line, on any function, I should say. So, for example, right here, this quadratic function, it is not a line, right? It's a quadratic. But we can still find the slope between these 2 points, and that is the average rate of change, okay? You can find that slope. Pick a point here, this point here, okay? So that's what this question's asking, to find the average rate of change between x equals 2 and x equals 10. So this point and this point, we're going to find the slope between these 2 points. X equals 2, right? X equals 10. All right? So the coordinate here is 2, 6, right? I just read that there, okay? And the other coordinate is 10, 22. Okay, I'll write those over here too because it's kind of hard to read them. 2, 6, okay? 10, 22. Aaron and Lauren, are you? Because I just asked Kaylee and Sierra to do it, to stop it, and they did, but you didn't. Do I need to specifically say your name? Please stop, okay? And look, guys, I mean, I understand. This is not the most exciting thing in the world. I know it's the end of the day on Friday, but we do have a test coming up next week, okay? I really just want you to understand this stuff. That's all there is to it, okay? Really, okay? So, we got our 2 points, slope formula, m equals, okay, y2 minus y1. So we're just going to literally plug them in here, okay, and then 10 minus 2, okay, slope formula. If you need to label them, label them. x1, y1, x2, y2, okay. 22 take away 6 is 16, 10 minus 2 is 8, and then what's 16 divided by 8 simplified to b? 2, okay. So our answer is right there, letter B, 2, okay. So don't get confused by the idea of average rate of change. It's literally just finding the slope between 2 points. Yes, even for a non-linear function, you can still find the average rate of change. This is the slope between these 2 points. Okay? We're going to do one more here, and then we'll just call it a day. All right? Last one right here. Okay? So in this case, we're not really given any sort of context here, right? We kind of have context. We have years, and we have percentages. Who knows what those percentages are of, but they're there. All right? We're asked to find the average rate of change from 1955 to 1965. Okay? So what are our coordinates? 1955 has a y-coordinate of what? 33.2, right? It's just right there in the column, or the row, okay? It's this point right here, okay? 1965, right there, right? And so we're just going to write that point out too, 1965, comma, 28.4, okay? If you need to, label your points, x1, y1, x2, y2, and then just do the arithmetic. I'll zoom in on that some there. So we'll do 28.4 minus 33.2, and then 1965 minus 1955. Okay? So 28.4 take away 33.2. Ooh, I got to use a calculator for that. Negative 4.8, thank you. Over, and then 65 minus 55 is going to give us 10. Okay? And so if you divide these two, yes, you get exactly negative 0.48, okay, which is A as an answer. Okay? If you want to get some more practice, there's a few more questions on the back. They won't be homework. Maybe we'll do those on Monday or something like that, okay? But I think we just need to call it quits because I've reached my limit too. All right, let's not line up, though. You can stay in your seats. You can stand up at your seat, but we're not lining up, okay, right? No more lining up. We forgot that yesterday.
They can stretch all